This is our third pulleys video, and as it says, it's pulleys on an inclined plane. So here's the situation. Mass A is at rest on a smooth inclined plane, and particle B, or mass B, is hanging down, and the question is, will there be acceleration in the system, and if so, in which direction? Well, first of all, let's put our forces on the diagram. There's the weight of A, the weight of B, a tension in the string at A, a tension at the other end of the string by the pulley, and then the vertical section of the string from the pulley downwards and from mass B upwards. And finally, A is in contact with an inclined plane, so there's a normal reaction. So those are all the forces that come into play. Now we're going to resolve the weight of mass A into its two components. So that will be the mass of A times, or the weight of A times cosine theta, and down the incline it will be the weight of A times sine theta. Now for mass A, parallel to the incline, the resultant force is T minus mag sine theta. That's assuming that the mass A is going to be moving up or accelerating up the incline. And therefore, using Newton's second law, that's the equation we'll obtain. In the same way for mass B, the resultant force, well, it's accelerating downwards, so it's the weight minus the tension, and applying Newton's second law, that's the equation we obtain. And we'll be using, once we obtain those equations, we'll be using them to either find the tension or find the acceleration, or find something that we need to find. So here's our example, and part A says find the acceleration in the system. So the weight of A, which is 2g, we're going to resolve that into its two components, 2g cos 30 and 2g sine 30, sine down the incline as a way of remembering. And then once we've put those components in, we can just eliminate the 2g weight from our force diagram. So in which direction does acceleration take place? Well, we've got a pull force of 5g vertically downwards here, and we've got a pull force of 2g sine 30 down the incline, and because 5g is greater than 2g sine 30, that will pull mass B down and pull mass A up the incline. So let's put our equations together for mass A. The resultant force, remember it's being pulled up the incline, is T minus 2g sine 30. Applying Newton's second law, that equals 2 times A. So force equals mass times acceleration. For mass B, the resultant force, that's being pulled down, so it's 5g downwards minus T upwards. And that, when we apply Newton's second law, equals 5 times acceleration. So those are our two equations. Add the two equations together. The t's, the positive t and a negative t, they will cancel out when you add. So we end up with 5g minus 2g sine 30 equals 7a. And dividing by 7 gives us 4g over 7 for our acceleration, which was what was given to us originally up here in the question. To find the tension in the string, well, from one of the equations we've already obtained, T equals 2g sine 30 plus 2a, and substituting in our value for A, we just end up with 21 newtons. Calculate the magnitude of the force on the pulley. So that's our force diagram. Those two T's are equal. 30 degrees to the horizontal. So we resolve this tension here. I'm going to resolve it into its horizontal and vertical components. There's other ways of doing this. I'm just using this one method. So it's T sine 30 downwards. So now it's equivalent, these two red tensions are equivalent to this blue system of forces, T cos 30 horizontally, and then T downwards from that tension, plus this T component here. So that gives us T plus T sine 30. And that equals 1.5 T. Putting our substituting value for T into those components gives us that. And so using Pythagoras, 36.4 newtons is the magnitude of the force on the pulley. Now, we're moving on to questions that look very similar, the only difference being that we have a rough incline plane, and so friction will come into play. Sources of forces, as ever, the weight of A, the weight of B, the tensions. I'm going to resolve the weight of A into its two components. Then I'm going to get rid of the weight of A. Okay. And now, in addition, friction. Now, the diagram tells us that B will be moving downwards, so A will have to move up the incline. It will be pulled up the incline. Friction will resist the motion that's trying to be made, so friction will act down the incline. If there was ever a situation where A moved down the incline, pulling B upwards, then the fact that A was moving down the incline would mean friction would be acting upwards, but not in this situation here. So for mass A, the resultant force is that, and then we would apply Newton's second law, and for mass B, that would be the resultant force, and once again we'd apply Newton's second law. So let's see this in a real example. So I'll give you a moment to read the question. So we have our forces in the diagram. Resolve the weight component, the weight into its two components, and that's 5g cos alpha, 5g sine alpha, and then I take away the weight. In which direction does acceleration take place? Well, 10g, which is the pull force down here, will always be bigger than 5g sine alpha, which is the pull force down here. So acceleration, the mass Q will accelerate downwards, and mass P will accelerate up the incline. And therefore, because P is moving up the incline, friction will oppose that motion, so friction will act down the incline. So for mass P, the resultant force is T minus the weight component plus friction. They're combining together to resist that motion. And that equals mass times acceleration using Newton's second law. Now, friction is at its maximum, mu r, because motion is taking place. So friction is mu r, and we're told in the question that mu is 0.2 and r must equal 5g cos alpha. If you have a look at the forces perpendicular to the plane, the normal reaction force r must equal 5g cos alpha. The reason that they must equal each other is because P is not moving off the incline. Okay, it's not moving into it, it's not being pulled into it, it's not being pulled off it. So these two forces perpendicular to the incline must be in equilibrium. So R equals 5g cos alpha times by mu, which was 0.2. And for mass Q, it's much more straightforward. The resultant force is 10g minus t, so we have 10g minus t equals 10a. So that's equation 1. That's equation 2. Now we can find alpha because we're told in the question that tan alpha is 0.75. So that's the 3, 4, 5 diagram, and therefore cos alpha is 4/5 and sin alpha is 3/5. And we can put those values now into equation 1. And we end up, simplifies greatly when we do. And equation 2 tucked underneath is just 10g subtract t equals 10a. We're going to add the two equations together. When we do, the t's will cancel out. 10g minus 19g over 5 is 31g over 5. And when we add the right hand sides together, we get 15a. So we can divide by 15, and that gives us our value for a. 4.05 meters per second squared. And to finish off, if we want the tension, which we do because that's part B of the question to find the tension, we just substitute our value of A into one of these two equations to obtain our value for T.